Welcome to the office. We want to take a look at an example of calculating a hydrostatic force, right? The force applied to a surface that has been submerged in some liquid. We'll be talking about water here again. So same thing that we've been considering, but let's take a look at our example, which is not accompanied by a diagram. Sometimes we'll have to draw these things for ourselves. Often we're given these, but here let's draw it. So what's the question? What's the scenario? We want to find the hydrostatic force on one end of a cylindrical drum. So we're looking at the end of a cylindrical drum. Cylindrical, cylinder, circle. So we're looking at the force exerted on a circle with radius 3 feet if the drum is submerged in 10 feet of water. Now, this is a little bit tricky because it doesn't clarify that this drum is laying on its side, but that's the assumption that we're going to go with. So let's draw the scenario as best as we can. I want to start off with our area that we're working within. So here is our view of the lake or whatever this drum is submerged in. And let's go ahead and say it's 10 feet deep. So we want this to be 10 feet. Excellent, so that's 10 feet. And if we have a radius of 3 feet, then that drum is actually going to be about 6 feet. So that's a little over halfway. So that's a pretty big drum here. Is this perfect? No. Does it need to be? No, not a big deal. Okay, so we have our drum sitting at the bottom of wherever, submerged. Excellent. So here's our scenario. We want to calculate the force exerted on the end of the drum. To do that, we often like to introduce coordinate axes, and we're going to choose these coordinate axes so that way we can easily express, right, these points, right? A circle. If I'm going to be working with a circle, I've got to have a relationship between my coordinates, right? My depth and how wide it is. So we're going to keep it pretty basic and just go ahead and introduce axes. Let me put these in here as red because these are things that I'm adding. And I'm going to follow with what the textbook does here, where I introduce our typical X and Y axes. Let me move this guy down just a little bit so it looks centered. And we're going to say that this is the positive X axis. So I'm going to put that in red like my axes. And this is the positive Y axis. Now, that does not necessarily agree with other examples that I've given, where I said the positive direction was down because we want to integrate with respect to the depth, right? From this depth to that depth, moving in the positive direction of depth. And this is okay. We'll get a relationship between Y and depth to help us understand what sort of substitutions need to be made in order for us to correctly integrate. All right. If I want to, I can now recognize that I can give the equation for a circle. So equation of a circle is simply x squared plus y squared is equal to r squared. And we're told that the radius in this case is 3. So I can describe the points on here as x squared plus y squared is equal to 9. So now I have descriptions for all of these points. All right, so I have an equation that gives me my points. I know how deep everything is. We should be okay for the most part. We just have to think pretty carefully at this point. So we'll continue to label this as we need to. All right, from here, I'm going to zoom in on our diagram a little bit. And I again want to recognize that I'm going to find approximations, right? If I want to find the fluid force on this surface, I'm going to do that by approximating it with rectangles right here. So if I can find the fluid force the approximate fluid force on this rectangle using right, the middle as an approximation for our depth. Then I can get the area, and then I can multiply by, let's see, the appropriate pressure. Right? Pressure times area is going to give us force. So let's remind ourselves of that a moment. Force is equal to pressure times area. And because we are working in feet here, we know we want to use the model where pressure is the weight density times the depth. And then we still have A here, the area. So we're going to use that the weight density is 62.5. There we go, 62.5. We want to use the depth will be given here, but we'll find that D is equal to something. And then we're going to also need to find out what the area is equal to as well. So area is going to be equal to something. We'll figure that out in a little bit. So we're going to need to make these substitutions. So it might require that we do some side work to get that, and that's okay. All right, so I have my rectangle. I need to find the area of this rectangle. I can, let's see here, I can label this distance as the change in y, because that's the change in depth here. And what we want to do is we want to then find this total width here. But that's a little bit hard to describe because that's going from the negative x value to the positive x value. Whereas if I just look at, right, if I think of this as our right triangle, I know that this side length is x and this side length is y. And y is the thing that I'm moving along, right? Because I'm going from here down to here as I make these calculations. My rectangles are oriented, so I'm stacking them and creating a stack vertically. So I'm going to be integrating with respect to y. So y is the independent variable in this case. So I want to have x written in terms of what that is, and then I can recognize that this total distance here is equal to 2 times the x value, whatever that x value happens to be. All right, so of course, right triangle, whatever the y value is, what is the x? Well, we gave the equation for a circle right over here. So if I want to, I can solve for x, right? I can subtract y squared from each side to get x squared is equal to 9 minus y squared. And then I can square root both sides to get that x is equal to the square root of 9 minus y squared. So this is convenient because that's going to give us, right, there's some details I'm skipping over. The square root of a variable squared is actually the absolute value of it. So we get 2 different x values here corresponding to this particular x value and this particular x value. So we get those 2 different x values. I choose the positive one so that way I can get this positive distance, and it is the square root of 9 minus y squared. So our total distance here, our width of this rectangle is going to be given by 2 times the quantity, the square root of 9 minus y squared. So I get this as our width, and our height is the change in y. So this gives me the area of the width is 2 times the square root of 9 minus y squared. And the height of that rectangle is the change in y. In this case, the depth, right? The depth we also want to express in terms of y. That would be really nice. So the depth is equal to, let's see here, this value. So I got to know where exactly this is, because here I have a y value, right? That's my y value, but that's not the depth. The depth is better described as, so right here, this is our depth. And of course, this value here, as said by this, is y. But what's this distance here? So maybe I'll label that over on this side. The distance from the surface of the water to the center of the drum is 7 feet. And how do I get that? Well, I know that the total depth is 10 feet, as described right there. And I know that the radius of the drum is 3 feet. So 3 plus 7 gives us our 10, or 10 minus 3 gives us our 7. So we can describe our depth then as, right, if we're here, 7 feet describes the center, we can subtract y, right? 7 minus y gives us our depth. So we identify the depth as 7 minus y. Excellent. Now, there's some interesting things that go on here. So I want to be really careful. I'm going to leave a little bit of space right here for some additional comments that maybe you don't need to write down, but will be really helpful in terms of us understanding what's going on. So I want to observe that I have the pieces that I need to get the force on our ith rectangle. Right, there's 10 rectangles. Force on the first, second, third, fourth, fifth, all the way up to 10. All right, I just choosing 10 arbitrarily. We want to take the limit as those changes in height go to 0, so it will increase the number of rectangles. So we don't know exactly how many there are, and that's okay. But the force on one of these guys is given by, let's see here, 62.5. That's the weight density of water times the depth of 7 minus y. And you know what? Maybe there should have been a little bit more space here. We'll see if we can fit what we need to write. But we're developing our approximation here. So our force on this is given by weight density, depth times area, 2 times the square root of 9 minus y squared. All right. That allows us to give us an approximation for total force as the Riemann sum, right? So our total force is going to be approximately the sum over the intervals of all of the forces, right, on each of those intervals, or rectangles, right? So this is the sum over all of the rectangles of 62.5 times 2 is 125 times 7 minus y times the square root of 9 minus y squared. Oh, and I forgot my change in y over here. Don't want to forget that. So this looks pretty good for us. This gives us an approximation for the total force. Now, we're not evaluating that explicitly. What we are doing, though, is we are applying the limit to obtain the integral. And this integral will give us exactly the force. So the force, I'm going to leave a little bit of space here. So the comments that I wanted to write above, I'm going to include here. So the force exactly is equal to the limit as the change in y goes to 0 of 125. Oh, I need that sum, but I can pull that 125 out. Sum over the intervals of 7 minus y times the square root of 9 minus y squared times the change in y. Excellent. So this is going to give us the integral, right? When I apply that limit process, I get the integral of 125 times 7, not 17 there, times 7 minus y times the square root of 9 minus y squared. dy. Now, I didn't include integration bounds right now. In all of my previous discussions, our positive direction, right, the positive direction of the variable we're talking about was the same direction that we wanted to integrate over. Okay, so if I want to integrate over depth from a depth of, let's see here, this would actually be 4 feet, right? 3, 6, this is 6 feet from the bottom, or 4 feet down. So I could say that I want to integrate from a depth of 4 to a depth of 10. So I want to, let me throw this in a different color here. I want to integrate from a depth of 4 to a depth of 10. But I'm not using d as my variable that I'm integrating with respect to. So it doesn't work like that. It works a little bit differently. So what I want to recognize is I need to make some substitutions. I already have everything written in terms of y here. Okay, I already have everything written in terms of y here. But if I wanted to, my integral would be from 4 to 10 of something d when I integrate from 4 to 10 with respect to the depth. But the depth is equal to, I said, 7 minus y, right? Depth is equal to 7 minus y. So this actually identifies a substitution for us that we have already done, but we have to make sure that we have the integration bounds correct. So this is going to give me, all right, let's see, depth, d is equal to 7 minus y. So d, finding the differential, this would actually be equal to negative dy. And we would have the integral from when d is equal to 4. Actually, let me get rid of that or move it over, whatever you feel you need to do there. I need to change my integration bounds. So when d is equal to 4, we have 4 equals 7 minus y. And that gives us y is equal to 3. 7 minus 3 is equal to 4. And when d is equal to 10, we end up with, when d is equal to 10, we end up with 10 is equal to 7 minus y, and y is equal to negative 3. So our integral becomes 4, gets changed to 3, and 10 gets changed to negative 3, and our dd becomes a negative dy. So I don't have a negative dy here. So I make one more substitution. When I change the order of my integration, when I want to integrate from negative 3 to positive 3, that introduces a negative sign, still integrating the same thing. And then this becomes, or this stays a negative dy, but very conveniently, we end up with addition and addition here, right? The negatives cancel out, so positive rather, not addition, but positives. So since I have a positive dy, right, our substitution, all of our work here would essentially yield that we integrate from negative 3 to positive 3, because there's actually some cancellations of negatives going on here before we can get this. Now that conversation is not included in the text if you happen to read the text, or depending on what text you're reading, I suppose. But the one that I've been referencing does not make that clarification. So we have obtained our integral, which is wonderful. We've given a good reason for our integration bounds, and everybody's happy. Again, the main thing that we want to keep in mind is when we're determining our integration bounds, our integral with respect to y is going to be from the negative to the positive, our normal thought for positive integration. But the direction of positive is the opposite of positive for depth, right? Depth, you go from 4 to 10, right? 4 to 10 increasing as we go from top to bottom, versus y is increasing as we go from bottom to top. So it doesn't match. When we, right, so we do two things here. The differentials are opposite of one another, and the integration bounds essentially are opposite of one another. So since they're both opposite of one another, when I make this substitution, I get a negative. When I swap the order, I get a negative, and those two negatives cancel, allowing us to still integrate in the positive direction with a positive dy. Okay, so if you ignore all those details, that's fine. I like to think of it in terms of integrating over depth. But we would have to understand our change of variables as we integrate over y. So we've set up the integral. If you're really happy with this, you can go ahead and open Mathematica, and you can evaluate this. So let's go ahead and do that. And for those of you that want to see the worked out integration, we will also do that. But that's going to double the length of this video. So we'll evaluate this using Mathematica at first, and then we will go ahead and do it by hand. So we want to integrate 125 times 7 minus y times the square root of 9 minus y squared. So that's what we're integrating. Oh, and I managed to write y minus y instead of 7 minus y. 7 minus y and 9 minus y squared. Okay, that looks good. All right. And then we are integrating with respect to y, but since it's a definite integral, we say inside of curly brackets, y integrate from -3 to +3. There we go. Excellent. So I just want to go ahead, hit enter, and I'm going to get a value 7,875 pi over 2. So if we are using our calculator or Mathematica, we get this 7,875 pi over 2. And if I want to, I can find the exact, or right, that's the exact value. I can find the approximation by asking Mathematica to, see if I copy that, I can just say capital N. And I don't know why exactly. I don't know what the reasoning for the capital N is. Maybe for number, right? I don't want an expression. I want a number. So I want to find the number of whatever this thing is. So then I can go ahead and hit enter. Oh, sorry, shift enter. And it's going to give me that value here. Now it ends up being precise enough. I wonder if I can change this a little bit. So I'm going to give the same thing, but I think I can specify the number of decimal places here. So if I go to 5 decimal places, it still says 0 there. Okay, well, it didn't give any complaints, but this gives us that it really is approximately that, right? We understand that pi is a repeating decimal, so this should not be an integer value. So 1237.0. So this is approximately, that's not quite what I wanted here. All right, let's grab this differently. Here we go. This is approximately 12,370, and this would be pounds. So if you want to use Mathematica, you're welcome to do that. Same thing here, we used Mathematica. You could also use your calculator. Now, if you want to see the details, keep watching. If you're satisfied, have a wonderful day. So I want to try to present the details on calculating, let's see here, the integral from -3 to +3 of 125 times 7 minus y times the square root of 9 minus y squared dy. And if I want to do this, the first thing I'm going to do is I'm going to separate this integral a little bit. I'm going to distribute the square root over this subtraction, and at the same time pull the 125 out. So this is 125 times the integral from -3 to 3 of 7 times the square root of 9 minus y squared minus y times the integral of 9 minus y, sorry, y times the square root of 9 minus y squared. And we're still integrating with respect to y. Now I can split the integral over the subtraction to get 125 times the integral from -3 to +3. Actually, I can pull that 7 out at the same time. The integral of the square root of 9 minus y squared dy, and subtract 125, right? That coefficient will carry along as well. An integral from -3 to +3 of y times the square root of 9 minus y squared dy. So what you might then do is notice a couple of things. This is an even function. So if f of y is equal to the square root of 9 minus y squared, then f of -y is equal to the square root of 9 minus -y squared, which is equal to, all right, when I square negative, it makes it positive. So this is the square root of 9 minus y squared, which is f of y. So f is even, which is fantastic, because then when I refer to my book, I remember that when I have an integral from a negative number to a positive, right, the same number, -3 to +3 of an even function, then it's just 2 times the integral from 0 to the positive number. So that, I mean, does it make a significant change? No, but it does give us a little bit of something. So 125 times 7 gives us 875 times the integral from 0 to 3. And instead of integrating again from -3 to 3, it's 0 to +3, and I multiply by 2. Still the square root of 9 minus y squared, so no change, of course, in the integrand. But I also, for this other function, if I let g of y be equal to y times the square root of 9 minus y squared, then I get, this is an odd function because g of -y is equal to -y times the square root of 9 minus -y squared. And when I square a negative, it becomes positive. So this is -y times the square root of 9 minus +y squared. But this is the negative of exactly g of y. So this is the negative of g of y, which means that this is an odd function. So g is odd. And since it's odd, we can say, oh, hey, look, for an odd function, when I integrate from -3 to +3, I get 0. So by distributing over the subtraction and grabbing onto this guy here specifically, we have successfully removed part of the integral and simplified the thing that we need to evaluate. So now our integral looks a little bit more basic. Excellent. So 875 let's see here. I end up with a 2. I didn't write down what 2 times 875 is, so let me do that a second. 2 times 875 is 1,750. So I get 1,750. And then I actually need to multiply that by, oh yeah, no. Yeah, that's what I need, 1,750. Excellent. So this is equal to the integral, that times the integral from 0 to 3 of the square root of 9 minus y squared. And I say to myself, how do I integrate this? Well, this should look pretty familiar. So we have an example in our notes where we talk about, hey, what do we do when we have the integral involving a radical of constant squared minus some function squared? And yes, constant squared, 3 squared, minus a variable, right, function squared. So this is exactly what we have. So what this would encourage us to do is recognize that number minus sine squared, right? 1 minus sine squared is cosine squared. So this encourages the substitution of letting the variable be sine and including an appropriate factor to handle the constant squared. So what I'm going to do is I am going to let y be equal to 3 times the sine of theta, because 9 is 3 squared. Then dy is equal to, yeah, we'll leave that there. Dy is equal to, let's see here, 3 times the cosine of theta d theta. And when y is equal to 0, we get 0 is equal to 3 times the sine of theta. So 0 is equal to the sine of theta. And sine of theta is equal to 0 when? Well, if you haven't been already reflecting back on, right, our trigonometry, you can go ahead and notice using the unit circle. This is what our book gives us, which is kind of hard to read. Sine of 0 is equal to 0 at 0 radians. That one works out kind of nicely. So you can also see that here, where our points are given as cosine comma sine. So I'm looking for sine to be 0. That is the second entry to be 0. And that happens right here and right here. So we say, well, which one do we want to use? Well, typically we use this one here. So we'll integrate from with sine of theta being 0 as 0 radians. And yes, we always work in radians here. All right, so this gives us that theta is equal to 0. Also, when y is equal to 3, then we get that 3 is equal to the sine of theta. 3 times the sine of theta. So we divide by 3 to get 1 is equal to the sine of theta. And again, we refer to our unit circle. When is sine of theta equal to 1? Well, specifically here, right, the second entry there is 1. The sine value is the second entry is 1, and that occurs at pi over 2. So we know that theta is equal to pi over 2. All right, from here, I have everything that I need to make my substitution. So this is equal to 1,750 times the integral from, now it's 0, 0 becomes 0, 3 becomes pi over 2, the square root of 9 minus 3 times sine of theta squared, and dy becomes 3 times the cosine of theta d theta. Now, once we have this, we are able to simplify. We're able to simplify this. So this is equal to 1,750. If I want to, I can pull that 3 out. So multiply by 3. times the integral from 0 to pi over 2 times the integral of the square root of 9 minus, distribute the square to get 9, times sine squared theta. And I still have a cosine theta d theta here. And now I want to go ahead and simplify the radical. So this is equal to 1,750 times 3 times the integral of 0 to pi over 2 of the square root of, pull the common factor of 9 off to get square root of 9 times 1 minus sine squared. And this is wonderful because I know what 1 minus sine squared is. And this is equal to 1,750 times 3 times the integral from 0 to pi over 2 of, I can apply the square root over, right? I can distribute the square root over. I can distribute exponents over. I'm trying to just say the same thing here. I can distribute the square root over multiplication. I can distribute radicals, the square root, which is a radical, over multiplication, or I can distribute exponents over multiplication. Those are the same thing, so that's okay. Square root of 9 is 3, and then I'm going to take the square root of, in this case, I'm going to replace the 1 minus sine squared with cosine squared. Excellent. Now, on the interval from 0 to pi over 2, I want to notice that cosine of theta is greater than or equal to 0. And that's worth noting because when I take the square root of a variable squared, it gives me back the absolute value of that variable. And in this case, cosine of theta would be positive. So the absolute value of a positive number is exactly that number. So 1,750, pull out the additional factor of 3 to get 9 out there. Integral from 0 to pi over 2. This becomes simply the cosine of theta, cosine theta d theta. Excellent. So we've reduced this to a trigonometric integral, and this is not so bad. So 1,750 times 9 times the integral from 0 to pi over 2 of cosine squared theta d theta. And we might say to ourselves, well, I'm not sure what to do, and that's perfectly fine, right? This is a learning process. So we go back to our lecture notes where we learned these wonderful things, and we scroll back to this section on what substitutions we need to make for trigonometric integrals. So I go back all the way to where I talk about involving powers of sine and cosine. And I notice that the third guideline gives me when the powers of sine and cosine are both positive and even, then I can use the power reducing formula. So I just have cosine squared in this case. So it's 1 plus cosine of 2 theta divided by 2. I'll write that a little bit differently as, oh yeah, I still wanted to go further. There we go. So 1,750 times 9 times the integral from 0 to pi over 2. So rather than having that whole thing over 2, I'm simply going to call it 1/2 times that was the numerator. And now I've already forgotten, that's okay. So 1 plus cosine of 2 theta. 1 plus the cosine of 2 theta. And now I can integrate these things without any concern. So this is equal to 1,750 times 9. Let's see here, times 1/2. I can pull that 1/2 out. The integral of 1 would be theta, and the integral of cosine 2 theta would be 1/2 times the sine of 2 theta. And I'm evaluating from 0 to pi over 2. All right. If you want some details on this guy, the integral of cosine 2 theta, that would require, if you want more details than that, it would require a u substitution. Of course, I wouldn't want to do that here because then I have to change integration bounds again, but we should recognize that that's the correct integral. And from here, I can plug in my pi over 2, and I can plug in 0 here. So let's see here. I included An additional factor of 2. Okay, yep. I'm liking this. So what I might do at this point also is recall that 1,750 was expressed as 2 times 875, I do believe. Yes, 2 times 875. The convenience of that is that I can cancel out the 2 and the 1/2. A little bit of simplification, not much. I haven't bothered to multiply some of this stuff out, so I could have left it all until the end, and that would be fine. Anyway, 875 times 9, whatever that turns out to be. So 875 times 9, plug in pi over 2, so I get pi over 2 plus 1/2 of the sine of 2 times pi over 2 is pi. So I'm taking this thing and I'm subtracting the evaluation at 0. So 0, let's see here. Yep, sine of pi, opposite. Okay, yep. Let's see here, 0 plus 1/2 times the sine of 0. So I'm trying to think here. Let's see. This looks good. The sine of pi. Oh, yep, that's 0, and the sine of 0 is 0. Okay, excellent. So 875 times 9, pi over 2, plus sine of 0. If we don't remember, we can go here. Sine of 0 is 0. 0. Sine of 0. I'm sorry, that's actually what I looked at a moment ago. Sine of pi, rather. Sine of pi is also 0. So this is okay. So it's a whole bunch of zeros. So this gives us 875 times 9 times pi divided by 2. Notice that this is not an even number. That's not an even number. So they don't contain a factor of 2. So there won't be any simplification. And this gives us 7,875. Yeah, 7,875 pi over 2. Yay! And that's the same thing that we had found quite some time ago using Mathematica. So this is a good example of also why myself and other instructors, of course, sometimes will say, hey, now that we have something that we should know how to do, let's just go ahead and say that we're done, because it makes the example a lot longer if we include all the details at times. So that'll be why I might do that in class. But again, as a supplemental video, happy to provide those additional details. All right, so that's all that I have for now. Have a wonderful day, and I will see you guys again back here in the office, in the workshop, or in the classroom.